So in most the questions we read on GCSE papers and just around, we see something like this. Something like to the nearest centimetre, measure to the nearest millimetre, to the nearest metre and things like that. So that means that numbers used in questions and things like that are often rounded, they're not the actual value. Therefore, when we calculate and do all our sums and get an answer, we might not be getting the most accurate answer we can get. We're getting a fairly accurate answer, but not the actual one because we've done rounding when taking measurements. Therefore, bounds, this topic is about the region in which the actual answer lies and how close we can kind of pin down that actual accurate answer to an interval. So, let's have a look at kind of introducing the theory of this and some examples before we move on to doing some exam questions. So this is a typical bounds example, just to introduce the idea. My weight is 50 kilograms to the nearest kg. Find the interval within my weight lies. So my weight might not be exactly 50 kg, it could be, but it's saying to the nearest kg, so kilogram. So the way to look at this is to draw out a number line. And we put the number that we have in the question, just put that in the middle. So we've got 50 kg. And we take, on this side, our next number, we do half a unit this side. So our unit is to the nearest kg, so 1 kg. So that means we're going to go half of that, so we're going to go, this is going to be half the unit we're measuring, it won't always be kilograms. So we're going to go half this way, so we've got 50.5 kgs this side. We're going to go half at an interval that way, 49.5 kilograms on this side. So that's the number line we're looking at. So, the nice thing about this is it does kind of make sense. So, for example, if my weight was 49.5 kilograms, that was what I measured it as. If the question had asked me to round it to the nearest kg, I would have written down 50 kilograms. So this could be my weight. My weight could also be in here, because if I rounded a value here to the nearest kg, it would also round to 50 kilograms. My weight could also be here, so it could be anywhere within this interval, so half a unit that side and half the unit this side. And it's asking me for the interval. So I need to basically put values on that interval there, just what part of the number line is that. So I'm going to call my weight W. So I'm going to say that my weight W lies in the region, so it can go from here to here. So it can be 49.5, because I know if I get a 0.5, I round up. So it has to be bigger than 49.5, or equal to, because if I land on a 0.5, I round up. And then on this side, it has to be less than, so this way, of 50.5. And this is very important. This one is not equal to, so please pay attention to these signs, because if I land there, we know that 0.5 rounds up. So if my weight was actually this value, 50.5, I would round up to 51 kilograms. So that's why we don't have the or equal to sign there. So it can be anything, like it can be just there. It can be as close to that line, but just not on that line as possible. So this is the interval in which my weight lies. I should probably add some units onto this. Okay, so I hope that makes sense. Please, please, please draw out a number line. It just, makes life a lot easier. So we're just working out this region here. So now we'll go through another example. Okay, so my calculator weighs 0.09 kilograms to the nearest 0.01 kilograms. What is the interval in which my the weight W of my calculator lies? So I've said that it's 0.9 to the nearest 0.01, so that means it could be 0.09, but it could also be something near 0.09. So let's have a look. So first thing again, make sure you draw out a number line and put your value it gives you in the middle. 0.09. This time our unit is 0.01 of a kg. So we go half a unit this way and half a unit that way. So half of 0.01, you can either do it on your calculator, is 0.005. So we're going to go 0.005 that way and 0.005 that way. So what we're going to get here, you can again, if it is a calculator paper, you can add that onto this value, 0.095, that side. And then on this way, if you take away half the unit, which is the unit this time, 0.085. And these are all kilograms. So I know that the weight of my calculator is somewhere in this part of the number line here. So it could weigh this, could be here, it could weigh this much, it could weigh this much. So I don't actually know how much it weighs, I know it weighs somewhere in that region. So let's mathematically define this region. So W lies in the interval, so it can take this value here, 0.085, because we know if it has a 5 on the end, it rounds up, so it would round to this one, because that's our next point on the number line with this interval. So it has to be bigger than that value, or equal, because these values round up with the 0.5 at the end, and it has to be less than this next value along our number line. But if we actually equal that, we would round up, because it ends in a 5, so we can't put the or equal to sign. It can be as close to that line as possible. Ooh. But if it was on that line, it would round up to, so this line would round up to 0.1. Okay, so we've worked out our interval and we've paid really close attention to that. So that's what I've got. Why don't we do, I've got my scales here, why don't we actually weigh it and see if it lies in that region. So the actual weight of my calculator is, oh, just changed, 92 grams. Okay, thank you scales, you've been very helpful. So that's in grams. To get to kilograms, you divide by 1,000. So kilograms here, we can do the column method. Grams. So 1 kilogram is 1,000 grams. To go kilograms to grams, I multiply by 1,000. To go the other way, I do the inverse. I divide by 1,000. I have 92 grams. I'm going this way, so I divide it by 1,000. So how many kilograms is that? And is it in our region? 0.092 kilograms is the actual weight, which yes, so 0.092, about there, that was the actual weight of our calculator. It wasn't actually 0.09, but it was within this interval because we've rounded it. So the way that they make it this harder in the exam is by putting it into doing calculations. So we're going to do 3 exam questions in which they've used bounds. Okay, so here we've been given the equation V equals S over T. That is to do with speed equals distance over time. But they've called speed velocity, and they've called D displacement, which is an S. But yeah, it's that equation. Cool beans. So let's actually read it. So S is 4.15 to 2 decimal places, and T is 2.516 to 3 decimal places. So they're trying to then mixing it up here. Work out the upper bound for V to 3 decimal places. So we know that V equals, copy out the equation, boom. And we want B, we don't want anything to do with B, we want V to be as big as possible. And there's a division in here, so it kind of gets complicated. So to get V as big as possible, I kind of think of V as something else. So let's say I had like a cake, and I want to get as much as I can. I want something as big as possible as here on top. So I want as much cake as I can get. I want the biggest possible cake I can make. And I want to divide it by, and bearing in mind I want a lot of cake, please. I want to divide it by as little as I can, so I get more. So I want to divide it by the smallest thing I can, so I end up with the upper bound, the most cake I can have. So let's say V is our cake. We want, V is the fact we want as much cake as we can. S is our cake, so we want as big a cake as we can possibly make, and we want to divide it by as little people as possible so I can have V, the most cake I want. Okay, so when it's division, it might be an upper bound, but that doesn't mean you take the biggest and the biggest. If you divide, you then take the smallest. So just try and relate it to something else, or just like think it through carefully. So just because it's upper bound, you don't take big and big. So if I want V to be as big as possible, I want big as possible on top, and I want to divide by like as little as I can so I can get the most myself. Bit greedy. So instead of writing big and small, we could write upper bound for S divided by the smallest for T, so lower bound T. So why don't we work out those two things? So let's draw a number line and let's look at S, 0.15. Okay, to 2 decimal places. So this is our unit this time. So we want half a unit this way and half a unit that way to work out our region. So we've got, on this way we have 4.155. So you just basically like add a 5 on the end. And then this one is going to be 4 point, and then you're going to have 4.145. So here you have 1, and then you have 45, 55, but don't think of it like that. So if I land here to 2 decimal places, I know that because there's a 5 in there, that's going to round this 4 up to 5, and then here it would round down. So our interval is this. We're not really looking for the interval, we're only interested in the upper bound for S, and this is our upper one. So we know that that is 4.155. So now let's have a little look at T. So on our number line, if we place T in the middle, and this is now to 3 decimal places. So we want half a unit this way and half a unit that way, and our unit being 3 decimal places. So we're going to have 2.5165 on this side, and so half a unit that way, 2.5155. And we can check that, because if we got this and we wanted to 3 decimal places, we would look at the 5. That's 5 or more, so this one would round up, so this 5 would become 6. So yeah, that's correct. So this is the interval in which it can lie, but again, we're not asked for the interval. We've kind of thought through this logically, and we want the lower bound for T. So we want this value here. So divided by the lower bound for T, which is 2.5155. So now you work that out. So 4.155 divided by 2.5155, and you get 1.651759, etc. And it's asking for 3 decimal places, so 1, 2, 3. So I look at this one. Yes, that is 5 or more, so that one's going to round up to 1.652. And that is V. Okay, so here we have given a triangle, and it's given us some information. So A is 4.1 centimetres to the nearest millimetre, so that's the decimal point after a centimetre, and C is 10 centimetres to the nearest centimetre. So first note, they are different. Calculate the lower bound for B. So as we can see, this is a right angled triangle and we're dealing with length, so we know that it is Pythag. So we're using a lot of knowledge in this one. So the formula for Pythag, it's already labelled the triangle for us, is a squared plus b squared equals c squared. Now we're after b, so I'm going to rearrange. So b squared equals c squared. I'm taking the a over, so it becomes minus a, because it's plus a on this side. Now I'm going to look at that, and I am going to try and calculate the lower bound for b. So I want the smallest possible value for b. So I want small here. Bearing in mind I can adjust C and A a bit, and I want to get the smallest output. So to get the smallest output, I want to start with something super small, like the smallest I can possibly make it, and I want to subtract something, and then again, it's not the smallest, I want to subtract something as big as I can possibly make it. So I want the smallest C value I can possibly get, subtracting the biggest A value I can get. Because if I've got something small, I want to subtract as much as I can to make it as small as possible. So again, be careful, just because it's a lower bound doesn't mean you take the smallest values for A and C. So we want the smallest C, so let's actually put that into maths terms. So we want the lower bound for C, and we want the upper bound for A. So it might seem a bit counterintuitive, you might just want to take the smallest values possible, but no. This is why it's quite, this is why it gets tricky. So, first of all, let's find the lower bound for C. So C says it's 10 to the nearest centimetre, so I go half a unit this way, 10.5, so half centimetre that way, and half centimetre this way, which is going to be 9.5. So that's the interval in which it can be, so it can be any value in here. We want the lower bound, so we're going to take C to be 9.5 centimetres. Okie dokie. What about, now let's have a look at A. Okay, so we're looking at A, so we draw this for A is 4.1 to the nearest millimetre, so that's this after the decimal point of a centimetre. So we go half millimetre this way, 4.15, and half millimetre this way, which is 4.05. Because I know, so you can do a quick check, if I got this value here, and I was rounding it to nearest millimetre, that 5 would take it up, so that 0 would become 1, and then that would go down to 1. What we're looking for, we're looking for the upper bound, so we want the big one. So we're going to take the value 4.15 centimetres. So now we can just plonk those two values in our equation. So we have b squared equals c squared, the smallest value for c though, 9.5 oops, centimetres squared, minus the upper bound for a, 4.15, and then we want to rearrange for b, so we want the square root of all of this side. And then it's saying to 1 decimal place. So the answer to that is b is 8.5456, etc. But we want it to 1 decimal place. We want it to here. So we look at 4, which is less than 5. So we don't round up. We leave it as 5, and then that is centimetres. So I hope you understand bounds now. Be really careful when it's just asking you for lower, that you don't just take the two smaller values when you're doing these sort of harder questions.